All right, we are given this problem of inclines, and we need to find the final velocity of the skier at the bottom. So a skier starts from rest at the top of a 20-degree incline and skis in a straight line to the bottom of the slope, a distance d of 400 meters. If the coefficient of kinetic friction between the skis and snow is 0.2, calculate the skier's speed at the bottom of the run. So what I'll do is I'll first draw out a free body diagram, or at least a representation. We know this angle here is 20 degrees, not 30 degrees, 20 degrees. We know the skier is going to be at the top, and we know the distance the skier travels down the slope is 400 meters. So what we can initially do is find the height here so we can find the gravitational potential energy of the skier. So the height here is simply, so let's do h is 400 sine 20. And if we pop that in our calculator, 400, we get 136.8. I'll just do 137 meters, round it up. 137 meters, 137. And now what we can do, now that we have the height, we can use the equation of potential energy. That's just mg delta h. And notice how we do not have mass given to us in this question, so we'll just assume that it's not necessary for calculations. So we could just shorten that down to gravitational times delta h. This question used 10 as acceleration for the answer, so I'll use 10 here. So again, we don't know the mass, so it's just 10 times delta h. Well, the change in height is 137 so we're basically treating the bottom of the slope as 0 meters. The change in height is 137. So that the energy here is just 1,370 joules. And so what we'll do is we'll just do GPE at top. So we'll set that aside because we don't need that for now. But what we do need to do now is calculate the energy lost due to friction, because this is not a closed system. If it was a closed system, there would be no friction. It would be frictionless, a frictionless plane, and you'd just be able to calculate work by like the normal and stuff like that. But this, we need to take into consideration friction. So what we'll do is calculate the frictional force. So I'm just gonna have the box here. Again, we do not know the weight or the mass of the skier, so we're just going to assume this is mg, mass times g. Mass isn't considered, so it's just 10 here. I'm just doing the values so we can kind of visualize, obviously, the different values we get. And what we need to do is find the normal, which is this, the normal force, which is this arrow up here. And we know that this angle here is 20 because the angle between the normal is always going to be equal to the angle of incline. So from here, we could just do 10 cosine or cos 20. And that gives us the normal, which is, it's going to be the same for the arrow pointing down and pointing upwards, which is why we're using cos. We're finding this length here, obviously because the skier is not flying upwards or going downwards. And so that's simply equal to 10 cosine 20, 9.4. I rounded it up. And so if we know the coefficient of friction as 0.2, we can easily use the frictional force equation, which is just coefficient of dynamic friction times normal force, and so it's just 9.4 times 0.2, and that's equal to 1.88 newtons. So frictional force is that. And what I first fell into when I was solving this problem was that I set this as the energy loss, but obviously force is not an energy, so we have to convert this to an energy. And we know for the problem that the distance covered is 400 meters, and we know that the frictional force, the force that resists motion in the direction the object is traveling, is 1.88. We can simply multiply those two together to get work, and that should get 752 joules. And so now you see the units are dimensionally correct. We have joules here. I should write that here. We have joules here, and we have joules here. So what we can do is realize that at the start, kinetic energy is 0. At the bottom, gravitational potential energy is 0. So along the way, energy is lost due to friction, and the amount of energy is 752 joules. So we do 1,370 minus 752. So I'll kind of know what we're doing here. N at base. So that's simply 618 joules. So that's the energy that's at the bottom of this hill. So right here is 618 joules of kinetic energy, and up here is, what was it, 1,370 joules of potential. And again, what we know is that when it reaches the height of 0, there's no gravitational potential energy. So we need to find the velocity, and we know that the equation for kinetic energy, so we have the kinetic energy, we just need to find the velocity. So the equation for kinetic energy is and we happen to know, so kinetic energy is half mv squared. We happen to know that the kinetic energy should be 618, so we can set that equal to half mv squared. And remember, mass is not given to us, so we can just consider that not an actual variable and do some rearranging to get square root 618 over a half should give you 35.2 meters a second. I rounded that, so yeah, that's pretty much that is the answer of the question. So again, an overview, we found the height, found the initial gravitational potential energy, then we found the frictional force to get the work done over the friction plane, the inclined friction plane. We found the work from the force times the distance, that gives you work. And then we found the energy, so that's the energy lost. We took away 1,370 minus 752 to get the energy lost throughout this journey. And so that gave us 618 joules at the bottom. And then we know that potential energy is 0, so all the energy that we do have is in kinetic energy. And then from kinetic energy, we can find the velocity by doing some rearranging. And yeah, I hope that helps.